Welcome back to Tailored Materials and Surfaces. Last time we were thinking about sol gel materials where a silicon compound formed into a cross-linked surface structure with some kind of connector on it and with an oxygen bond, silicon-oxygen metal bond to our surface, typically. And today I would like to think about how we would turn this into more of a solid material, which we would do by a thing called sol gel chemistry. Why might we want to do this anyway? Well, we can see that this compound that we were using to coat surfaces with is excellent for connecting an inorganic material, the silicon, to an organic material, whatever we connect to this double bond, for example. So we can use that in a further process to, whoops, camera's wobbling around. We can use that in a further process to generate something that is somewhere in between a polymer and an inorganic material, somewhere between a polymer and a ceramic, which we can then use in situations where a polymer is too soft and a ceramic is too hard. Let us think about the chemistry first. So how is this process going to happen? We've got some silicon with an ester or ether bond. It's a silicic ether, but it behaves more like an ester as we had last time, but we're going to do it again this time because some people might not have seen the last one. So we're going to attack this bond and it's going to behave like an ester, which means we can attack the silicon with a nucleophile and an ethoxide, in this case, will drop off and it will either pick up a proton or it won't, depending on the pH and depending on the solvent. So let's have water attacking, for example. It's often the case. And if water attacks, it's not a very good nucleophile, but it's good enough. If water attacks, we'll end up with a positive charge here. So we've got a hydrogen that could leave. And we end up with a negative charge here, which in this case will tend to be transferred to the ethoxide ion to make it leave. And then we'll end up with the trisilicic acid with this organic group on one side. Just as with an ether, this process is increased in speed by attacking it with a hydroxide ion, so having a basic condition, or by protonating first at this group, so having an acidic catalytic condition. So let's have an H here, and let's put an H on here and make this plus. If this is the starting condition, so stage 1, then we can attack it with some water and make the ethanol leave, and ethanol is obviously a much better leaving group than the ethoxide ion, which is not a great leaving group. So we can make the reaction go faster in both acid and basic conditions, and that is a characteristic of this reaction. So if two of these activated silanes come up to each other, put the pen down, then we have the same situation where one of these is effectively going to act as a nucleophile and the other one's going to act as an electrophile. So eventually we can have our 5-membered silicon, we can have our 5-membered silicon for a little while, and then this hydroxide is going to come off, and we can promote that reaction by either making conditions so basic that this one is deprotonated, so it's an anion, and that will release a hydroxide anion in the end, or we can make it so that this hydroxide is protonated beforehand, which makes it positive, and that makes this silicon a better electrophile. So we can either improve our nucleophile strength or we can improve our electrophile strength. It's difficult to do both because they're the same chemical. So when we get, when we get to a trimer like this, a linear trimer, we can see that one of these is not the same. So the two end silicons are the same and the one in the middle is different. The ones on the end have 2 OHs, and the one in the middle has 2 OSIs effectively. And what that does in this case is it changes the pKa, it changes the acidity of the things that we're interested in, which would be this proton, which is the same as the others, and this proton, and also this lone pair, and this lone pair. Because we're either going to protonate onto here, or we're going to deprotonate from here or here. That's the possibilities. So if we make it acidic, it will try to protonate one of these OHs, and the one with the, so we're trying to protonate it, the one with the highest pKb or the lowest acidity will become protonated. And if we want to deprotonate it, the one that's most acidic will deprotonate in the base condition. And it turns out that there is a slight difference between these two. So because they're on the same molecule, one happens first and then the other one happens second. It's enough that they're somewhat separated, so there is a difference. What we see is that these bridging oxygens pull away more electron density from the silicon than the OHs, and that means that this hydrogen is more positive because this electron density is pulled towards the silicon and back out to these, and that makes this one then more acidic. So if we put it into a base, this is the one that reacts, the one in the middle, and we tend to get more cross-linking because the more substituents there are on it, the more it tends to react. So in a base, we get ones that react tend to react more, and in acidic conditions, it's the opposite. These ones are more likely to protonate. Sorry, I got confused there. This one is more likely to be protonated than this one, and that makes acidic conditions more likely to make a very long chain, basic conditions more likely to make a cross-linked chunk of material. So far we've had one substituent that is not cross-linking, that's not able to react, so an alkyl chain. And if we change the size of that alkyl chain, we can limit what the molecule can do. So in this case, we've got a tertiary butyl group on there, and I've been trying to draw it but failing. We can make, or it self-assembles effectively into little cubes of silicon, oxygen, silicon, with another one in the other direction, so in the other dimension, turning into a cube with one of these tertiary butyl groups on every corner. And then it stops because it can't get any further because this is too much sterically hindering. It varies what we put on there, so we need to be a little bit careful on how big and how in the way our organic thing is, and also we will have a problem with hydrophobicity. So if we want to do this reaction, what we end up with, I keep saying so, that was what distracted me. If we want to do this reaction, we want to start with some kind of silyl ether with this oxygen in here that's going to behave a little bit like an ester, as we've mentioned before. But as we know, rub that out while I'm here. As we know, ethers and esters both behave quite hydrophobically. This group is going to dominate. This oxygen is not very polar, so the lone pairs aren't very available to do bonding. So it appears to solution like a very non-polar liquid. Then we've got water that we want to mix with it, and we're going to have some acid or base. I've put plus acid, but we're going to have some acid or base in there. If we put acid in there, it's going to form long chains. If we put base in there, it's going to try to solidify fairly quickly. So they behave differently in how they react, but we'll get the same product in the end chemically. But we have a problem. So we've got a non-polar thing. We want to mix it with some water. We need some kind of intermediate. If we put in something else, let's have some methanol. MEOH. If we put some methanol in, we generate a new problem because the methanol can also substitute for the ethoxy group here, forming the methoxy group instead, and the methoxy group has different reactivity, so we make the reaction more complicated. So let's not do that. Let us use ethanol instead, just to make our life a little bit easier. Because if we do that, then if it substitutes, it just makes the same thing. In practice, well, you often use a different solvent, but for thinking about it, it's easier, then less things happen. So we need this to dissolve in here, and it's not going to. If we start to mix it, however, we will start to hydrolyze things. Check my fingers off. So we hydrolyze one off to the single acid group, the single silicic acid, and we end up with this. And this should remind you of a soap. We've got 3 non-polar groups and 1 polar group. If we hydrolyze another one off, let's have this one, we end up with 2 polar groups and 1 non-polar groups, because the OH is going to behave quite a lot like water, like a non-charged soap, and these are going to behave like a not very long fatty acid, so it's like a not very long soap, but this is going to behave in such a way that it causes the silane to dissolve in water. If we add ethanol to it, it will help it to dissolve. If we don't add any ethanol to it, it will form an emulsion or a mixture. So that's the pre-polymerization. When we polymerize it, it will go back, because these are the reactive groups, it will go back to being more non-polar, and it will tend to phase separate back out of the solution and push out all of these other things which will be made. And we need the water in there we end up with the water in there. We need the water in there to hydrolyze it, and we can't take the water back out again, because when it cross-links, the water falls back off. So we end up with the reaction generating water. So we have a problem in that we will automatically have a 2-phase system, will automatically have complicated stuff going on. It's just how the reaction goes. Okay, so when our chemical starts to react, it will then form a non-polar substance. So first of all, it will be not mixed as a non-polar substance. It will form a soapy polar substance and mix with the water, ethanol, whatever it is, mixture, and then it will form a polymer, which is then non-polar again, and will tend to demix from the solution. And now we end up with 2 possibilities. So in the simple possibility, we don't have very much, and so it will form a blob. It will form a blob as either a liquid, so as an emulsion, just like just like oil in water, just like milk. So it will form a small blob, solidify. The other possibility, if we've got a lot in there, is that something more exciting happens. That we will try to, or effectively we will be making on a molecular level, a non-polar thing that is perfectly mixed with a polar liquid. And so our starting position will be very unhappy thermodynamically, and will try to revert, because of surface energy, because of the interfacial energy between the two, it will start to revert to a non-polar liquid and a polar liquid separately, or a non-polar solid and a polar liquid. But it will do that over time. So what we're interested in at the moment is the initial stages, and we can imagine that if we set up some places that form the non-polar substance, that's this net here, we generate an interesting structure that is called a bicontinuous network. So in this case, we've got a continuous network of this non-polar material, and then through these holes, so in the other dimension, we've got a 3-dimensional net. So this also has posts going in this direction, and another layer of this on top, and another one on top, and another one on top. So there's a stick of water and ethanol going through this way, one going through this way, and one going through this way. And if we manage to model them together in our minds, I know it's difficult, I can't draw it. I tried to draw it, if I failed that as well, actually possibly slightly worse than I failed the chemistry drawing. If we take this, we end up with 2 networks that look very similar. They're not quite the same size, because there's no reason why this dimension should be the same as this dimension. It doesn't have to be. It depends on the proportion of liquid and other liquid, the two materials in there. What this should remind you of is a zeolite. Okay, so this is what a zeolite looks like. It comes from prattlezeolites.com. So this is what a zeolite would look like, and this is the molecular equivalent of a bicontinuous structure. So here we've got the whole. This is the molecular bonds in this case. So it's a very, very small version, and we have these bonds going in a square network and square across. This is the kind of molecular sieves that we were using in organic chemistry, that you can use in organic chemistry to absorb water or to absorb specific chemicals, because you can control the size of these pores by the exact nature of the zeolite, how you cook it and how you add the different components. But in this case, the structure of the sol gel reminds us of this in certain ways, because it is very similar. It's not as regular, it's much more random, and it's much bigger, but it is very similar. Okay, I made myself look a little bit more healthy. I noticed my teeth disappear. Never mind. So what do we have? We can make this structure, and depending on how fast it sets, we've got a liquid, it's going to turn into a solid. Depending on how fast it sets, this grain structure will develop to a certain size, because if we wait for a very long time, it will turn into two layers. If we have two liquids and we manage to get it into this state, it will eventually phase separate and become an oil and a watery phase. But during this time, it's also solidifying, and so it will stop and end up with a porous solid, which is really useful for a lot of things. If we want, for example, to make a chromatography column, this is an excellent way to do it, because the liquid can go all the way through, and yet the solid is connected to itself, which means that if we compare it to a packed column where we've taken some particles and shoved them in, it can't compress because it's all one piece, so the pores are less likely to collapse. If we drop it, it won't move around unless it cracks. So it will behave a lot better, and we can have better control over the pore volume, because these are fixed. So we can make big pores in there and not have very much solid, or we can make small pores in there. Whereas if we have particles, we would have to mix small and large particles, and we're very limited to the amount of hollow space that we could have. They tend to pack quite tightly, and then we end up with not as many pores as we might like. If we do it this way around, we can have pore volumes of 75, 85, 95% plus. We can get up to over 90% pore volume, and then we end up with something that's called an aerogel, which is so light that you can barely feel it. So at this point, we've got a solid with a liquid in the pores. So pour a solid with liquid in the pores, and the solid isn't very dense. It's got these silicon-oxygen-silicon bonds in it, but it's also got some spare ether bonds in it, silyl ether bonds, because we haven't hydrolyzed it perfectly. It's also got some OHs, which is behind my head. It's also got some OHs, like this one up here, left over, so it's not perfectly solid. And when we try to dry it, it's likely to deform. If we take something that's like a capillary, a pore, and we put a liquid in it, and we allow it to evaporate, it forms a meniscus that's evaporating. And the meniscus has surface tension, and it's pulling inwards, and there is a net, because it's all the way around, there's a net equal tension in the lateral direction, but all of these are pointing slightly inwards, and that tends to crush our little solid and close the pores, which could be good if we want very dense material, if we don't want too many pores. It could be bad if we want to keep the pores and have a high pore volume. So how do we deal with that? Well, there's a problem. we need a liquid that has a very low surface tension. And so we are starting in a really bad place if we have water in there, because water has one of the highest surface tensions of any liquid. Apart from liquid metals, it's the highest. And if we evaporate a mixture of alcohol and water, we'll end up eventually with mostly water, because the alcohol will preferentially evaporate in a kind of unregulated distillation. And then the water will provide a very strong force to crush our solid, and we'll end up with an undefined, small pored, but crushed pored material. So we would like a liquid that has a very low surface tension, and one of those would be something like ether. If we substitute the liquid for ether, then we will end up with a smaller force, because the surface tension is very tiny. Oh, I can't draw it tinier because I drew a small one to start with. Let's draw a big one for the water then, and a little one for the ether. So we can have a smaller crushing force, and the alternative, the better alternative to that, would be to use a supercritical liquid which has no surface tension whatsoever. So we could imagine filling this up instead with supercritical carbon dioxide, which is a liquid, and then allowing it to evaporate above the critical point where the liquid turns into a gas without having a meniscus. It doesn't actually have a surface and just evaporates. We can try to have a look at that in the lab, I think. But yeah, let me write down, and I'll do that. We can try to have a look at that in the lab. We can try to make one of these sol gels in the lab so that you can see what's going on. And we will allow them to dry, and you can see that they shrink quite a lot, as in to maybe half their volume, depending on what the size is. The other thing that we can think about while we're doing this is how to densify this substance. So we would like to make these parts of the molecule, the supermolecule, react with itself. So to close up and make a more dense solid. And what are we going to do that? The simplest way to do that is to heat it up, and that will motivate the ethanol, in this case, and the water to leave. So it will generate a driving force, and it will also make the solid wobble around a little bit more to give them a chance to find each other. So that will increase the rate of reaction. We do have to heat it up significantly, however. So we would typically expect temperatures of 180, sometimes significantly higher than that, depending on how much of a proportion we want to get out. If we want to get it all out, we have to go to very high temperature indeed. So if we're making an optic fiber, for example, that's made out of silica, and we make it in this way, which is how they're made, by the way. So the reason for that is that you can then choose your glass exactly, because we're using a pure chemical that is distilled. So we can take our silica and silicon effectively, and we can make it into the shape that we want, and then we can make our optic fiber out of it and control fairly exactly what chemicals are in there, to a higher extent than if we dig up some sand and try to do it that way. If we do this, however, we have a problem of getting rid of the hydrogen, and that's a problem because the OH band tends to absorb some light, so it causes trouble, and we would like to therefore substitute it with something else and cause as much cross-linking as possible to get perfect glass. And there, in that case, we would have to heat it up to a very high temperature indeed. It's up to nearly 1,000 degrees. If we have these in here and the pores closed, then there is nowhere for them to get out. So if we have, for example, this ethanol group in there, the ethoxy group in there, and our material densifies and closes, because heating it up will also cause it to shrink, but not anymore under the surface tension of the liquid in the pores, but now under its own surface energy, because it gets soft when it's hot, particularly if we're going to heat it up to nearly 1,000 degrees. But even if we heat it up to a lower temperature and have these organic chemicals in here, it will start to soften and then collapse. And at that point, we might, depending on how we do it, we might end up with trapped organic things in there. And anybody who's ever done glass blowing will know that that is a easy thing to do. If you take some dirty glass and you heat it up and melt it, and you trap some carbon in there, the carbon burns and becomes graphite, so it turns black. But it can't escape anymore because there's no oxygen, free oxygen inside the glass to oxidize it up. And so you end up with a black mark inside the glass. This is obviously not good if you're trying to make an optic fiber. One of the things that they do to try to avoid that is substitute these with fluorines and heat it up extremely slowly to try to get as much of the other chemicals out as possible. And also they try to convert it in the liquid phase, for the quartz, for optic fibers particularly, they try to convert it in the liquid phase so much as possible to the hydroxide group so that there's less to escape. Whereas if we're trying to make a solid gel for other purposes, we might not do that. It might not also be as easy. If we have a side chain on our silica, we're less likely to get it as dense because it's going to be in the way. But one of the things that we can do at that point is we could have a disilane. So we could have a silicon with we can have an organic molecule with two silicons on it. So we can use that as a cross-linker effectively. And now we've got an organic-inorganic hybrid material, which is cross-linked all the way through. We could also have a double bond on there and we could do a different reaction to connect them together. But we would have to worry about the different temperatures that the different things can put up with. However, this is a common thing that is used. So if you go into the supermarket and you find a ceramic frying pan, this is what they're coated with. Not this exactly, but this type of material with a metal, with an inorganic center connected to an organic material, some of it being cross-linked and some of it sticking out the side. That's why it has a low surface energy, because it's got an organic material on it, and that's why it's very hard, because it's got the inorganic material in it. These materials tend to be difficult to remove from surfaces because we've got the silicon oxygen or the metal oxygen something bond that's very sticky, and we've got a single molecule effectively covering the whole surface, and we've got both organic and inorganic. So if we find a condition that will dissolve the silicon, hydrofluoric acid, very strong base, we can get rid of the silicon that's on the outside, and then we end up with an organic layer, which we can't get rid of with either hydrofluoric acid or a very strong base. And then we would have to go to a different condition to get rid of the organic material, and then we get an inorganic layer at the surface, which is then resistant. Likewise, if we attack it with something that's going to cause it to crack, we will tend to crack the inorganic material because it's more brittle, but the organic material will bend, and so we'll tend to not break it as much. So this is obviously a suitable material for a tooth implant or for similar items. It's also very good as the top coating of a frying pan because it's wear resistant because of the hardness of the inorganic material, but also slippery. Okay, so I've introduced you to solid gel materials. When I get into the lab next time, I will make one for you and show you how it's made. We'll make a simple silicon one, bearing in mind that we don't have to always use silicon. That was an example here. Titanium is often used as the inorganic component, or zirconium. They're both also hard and have different properties that we might want to use. So titanium has a high, or titanium oxide has a high refractive index, so it tends to be white, appear white. Zirconium is comparatively hard compared to even silica, even aluminium oxide. So we can make a harder material with zirconium particles in, zirconia particles in. And the organic part can also be substituted with fluorine molecules to make it lower surface energy if we want to. Right, let me stop there. No. So what I'll do is I'll go into the lab and I'll do that, and I'll try to get in and do a supercritical demonstration. I think there's a film on there on my YouTube site. You can have a look for that. There's one where I make some carbon dioxide go supercritical, but it explodes, which isn't exactly what I want to show you here. What I want to show you here is that as you pass the supercritical point, the carbon dioxide has a liquid phase at the bottom and a gas phase at the top. As normal, any liquid in a closed container will do that, but as you heat it up, it very rapidly, so the transition is fairly quick. It forms a diffuse interface, so you could still see that there's liquid at the bottom and gas at the top, but in between it there's not a line anymore. It just goes into a weird blurry bit, and very shortly after that the whole chamber just looks the same. This is the supercritical transition, and what's happening is the surface tension is going down and down and down, and then it just disappears completely, and we get just one phase, which is neither liquid nor gas. It's just a very dense, well, it's effectively a very dense gas, but there is no pressure that we can apply to it that makes it turn back into a liquid. It just stays like it is, filling the whole volume, but being filling the whole volume effectively. So you can change the pressure and you just change the distance between the molecules. There is no liquid, which is good, because then all we have to do is effectively increase the size of the chamber by opening the tap, and that will let carbon dioxide out slowly, and anything that is filled with the supercritical carbon dioxide will just lose it slowly and not be destroyed. These pieces of equipment are also used for preparing biological samples, for example. That's where we will try to borrow one from the Life Science Department to have a look at that.